Thanks everybody for showing up early again. I just want to point out one thing. Yesterday I had a typo on my slide. I had the wrong reference here. I'd copied in Young and Levenglick, but that's not this result. This is due to Smith and Young. And thanks to Ariel for pointing it out. Okay, so let's move on from maximum likelihood estimation. Let's get to something that's actually computational. So as we've seen, there's a couple of rules that we've introduced that are actually NP hard to compute. It's NP hard to compute the aggregate ranking or the winner. And so particularly I want to focus on Kemeny. Slater will kind of come for free. So if you remember, Kemeny is the rule where what you want to do is you want to find the aggregate ranking that has as few pairwise inconsistencies with the votes as possible, right? Summing pairwise inconsistencies over both pairs of alternatives and voters. And the Slater rule, what it tries to do is it comes up with an aggregate ranking that breaks as few of the pairwise election results as possible, right? So if A defeated B in a pairwise election and the aggregate ranking actually puts B ahead of A, that's one disagreement there. Slater tries to minimize that, but it doesn't look at the size of the pairwise victory. Okay, so it doesn't care whether A defeated B by 1 vote or by 100 votes. It just cares about what the overall outcome was. So for both of these, hardness results are known. They're maybe a little bit stronger for Kemeny. Actually, I'll show that in some sense, computationally, Slater is a special case of Kemeny. So we've talked about all these rules that are based on pairwise elections. Kemeny turns out to be also interpretable in terms of that pairwise election graph, right? Just like Borda, where with Borda maybe it wasn't initially obvious that you can compute the Borda winner just from that graph. It turns out you can, and similarly, it's the case for Kemeny. And the way to think about it is like this, right? So we can take our pairwise selection graph with the weights, the majority graph, and of course, if it doesn't have any cycles, right, then it will already correspond to an order, right? We just take the top element, remove it, the next one, and so on. So the only problem is really when there are cycles. And so one way to think about the rank aggregation problem is we try to turn this into an acyclic tournament graph, right? So a tournament graph means that there is a directed edge between every pair of alternatives. Acyclic means it has no cycles. If you have an acyclic tournament graph, that's exactly a ranking. Okay, so the goal is to take this graph happens to have some cycles like A, B, C, and to try to turn it into something that doesn't have cycles anymore, right? So we have to change something. We have to flip some edges. And if you think about it for a while, what Kemeny ranking is actually doing is it's trying to minimize the total weight of the edges that you flip in order to make the thing acyclic. Okay? So I'll give an explanation of that in a second, but so are there any other cycles in this graph that you see? I pointed out A, B, C.
A, B, D, C.
Sorry?
A, B, D, C.
A, B, D, C. That's also true. There's a simpler one.
ADC.
ADC. Right? Okay. So how can you turn this thing into something acyclic? What do you need to flip? And well, really we'll be interested in what's the best way to do it. Right? So how can we flip as little weight as possible and get the thing to be acyclic? But if you just see any way of doing it, that's fine too. Right, so yes, Christian.
Flip the AB edge.
If you flip the AB edge, okay, you can do that. Now you're still going to have ADC, right? But maybe we're making progress, right? I'm sorry?
AB and AB.
If you do AD and AB, yeah, that will break both of the cycles, actually. And so at that point, you can see that, well, A has become the last ranked candidate, right? Actually, this is the optimal solution, so let's just look at it here, right? So here we have this solution, and you can see B now is the Condorcet winner. Well, if this were the real pairwise selection graph, then D is next, then C, and then A is last, right? And so this is flipping a total weight of 4. Turns out you can't do any better than this here. What would have been another solution? Not as good. Yeah, you could actually flip AC. That would be flipping a weight of 10, so that would be worse, right? but it would work, and then you would get a different ranking. Okay. And if you think about it, the reason that this gives you the Kemeny ranking is if I put B ahead of A, then that gives me 2 more votes that I disagree with on A versus B, right? So that's the cost. So the cost of every edge to flip is exactly the weight on it. If you remember our graph that we had yesterday, it's gone now, but I think we had 1 3-cycle and 2 of its edges had weight 1, so we could have flipped either one of those. So there were 2 different equally good Kemeny rankings there. Okay. Slater turns out to be even simpler. You just throw away the weights, and now you try to flip as few edges as possible to make it acyclic. Okay? And in that case, of course, this other solution that we just saw of flipping the edge from C to A to C is the optimal solution. Right? And from this you can see that in some sense, from a computational viewpoint, Slater is the special case where you just ignore the weights of Kemeny. Okay, any questions about this? So both of these turn out to be NP-hard. Actually, this problem of making a graph acyclic is known as the minimum feedback arc set problem. So that tells you that it's hard right away. One interesting question for a while was, well, is this problem still hard on tournament graphs, right? Because typically, the input in a Slater problem is going to be a tournament graph. You have an edge between every pair. The only exception is if it's an even number of voters, you might have a tie and then one of the edges is missing. But if you have an odd number of voters, your input is always going to be a tournament graph. And so for a while it was open whether that problem is still NP-hard, but it turns out it's still NP-hard. Okay. That being said, sorry, question.
Is making minimal changes on the graph so that we don't have cycles equivalent to making minimal changes in the original preference such that the corresponding graph has no cycle?
Ah, interesting. Let's see. So you're saying make as few changes in the original preferences so as to make the whole graph acyclic. It's a little bit like Dodson, right? So Dodson, you try to make as few changes in the preferences, not to make the whole thing acyclic, but just to have a Condorcet winner, right? So like that part of it is acyclic. Off the top of my head, I'm not sure whether there's a name for the variant where you make the whole ranking acyclic. Do you know it, Ariel? No. Okay, that's interesting. So it might coincide with something else, but I'm not sure. Interesting question. Right. And here, of course, we assume we have the full freedom to flip any amount of weight, but you may or may not be able to directly do that in the preferences. Like if you have adjacent alternatives in the preferences, then you can, like, if you have enough preferences that you can always find for every pair a place where they're adjacent in every order, then it would be the same. But that's a very limiting case. So yeah. Good. Okay, still we want to solve these types of problems, right? I mentioned to you that we actually used the Kemeny rule for Duke graduate admissions, and there we had something like, so we had a lot of applicants, but in the final round, I think we had like 150. So we still wanted to be able to scale to that. And it turns out that you can do that just by integer programming. How many people know what an integer program is? Just, okay, good. So pretty much everybody. Right, so an integer program is a linear program where some of the variables or all of the variables have to take integer values. And actually, just to get everybody awake, maybe it's good to actually try to come up with this integer program on the spot. So what would be natural variables in this integer program? Yeah, Christian. A variable for each edge. Okay, good. So for any pair of alternatives A and B, we'll have some variable XAB. Right? And let's say that XAB is 1 means that A is ahead of B, right? In the final ranking. Good. And these are really all the variables that we need, because once we know all of these, then we're done. But we have to make sure that these variables are set in a consistent way. Okay, so what kind of constraints do we need on this? So if you... Sorry. Transitivity. Okay, sorry, who's speaking? Ah, okay. So how do we do transitivity?
A
Okay. So how do we encode that in terms of the integer program? But that's good. We do need that, right?
Say that A4B is set as 0 or 1?
So A before B is XAB is 1, let's say. Right? So XAB equals 1 means that A is ranked ahead of B in the final ranking. I mean, we could do it the other way, but let's just do it this way. Okay. And, right. So we need a transitivity condition, right, which says that if A is ahead of B and B is ahead of C, then A better be ahead of C. Right? That's going to be one of the constraints. The question is how to actually put that together. And we'll need some other constraints, and we'll need an objective as well.
Maybe so if A, like X, AB plus X, BC.
Okay.
So that's 2, you need the one. So
Sorry.
that's smaller than, yeah, smaller than, okay, it's XAB plus XBC. So that's
Oh, sorry.
smaller than XAC plus 1. Or like, not smaller than.
Smaller than,
Not larger.
I think, almost. 1
Plus 16.
1 plus XAC. Okay, I think this might work. Let's see. So this is saying, okay, if you set both of these to 1, then it's forcing this one to be 1 as well. If one of these is not set to 1, it's not forcing anything on this. So that will work. Okay, good. What else do we need?
XBA is 1 minus XAB.
Yep. What else do we need? So this will actually give you a ranking if you just have this, right? It will not have any cycles because of the transitivity. What's that?
The current state, the current, somehow put inside the current votes that you already have.
Yeah. Nothing that we have so far is actually taking the votes into account, right? That's kind of a problem. By the way, I should just bring the picture back up. It'll be easier to see. Which makes sense, right? So far what we've written down is just that the result had better be a ranking, but it doesn't say anything about the vote, so that has to come in. Yes.
Can we do the what's the objective?
Okay, good.
C sub AB times
So what is C sub AB?
times X AB
Times X.
the sum overall AB.
Okay, so what does CAB mean?
That would be the weight on the edge.
The weight on the edge, right? Oh, sorry, let's go back to Kemeny, just to really have it. So are we getting the direction right here? Right, so CAB in this case would be 2,
So
right?
we want to invert it if it's already selected.
Okay, good, because so the one problem with this is that this is, if XAB is 1, and then you're actually agreeing with all this weight, right? And we tend to want to agree. Just the way that we set things up, XAB means that we put A ahead of B, but that means that you're actually agreeing with all of this weight. So that's kind of a good thing. There's different ways to fix it. You can maximize, or you can do what I think Christian just suggested and flip this over. So you could do this, right? This should work, right? Because now it's saying if XBA is 1, then you're disagreeing with all the weight that goes the other way. And so we try to minimize the total weight that we disagree with. Good. Okay, so that's all. And this turns out to scale. It depends on how you generate your instances. If you generate instances completely at random, it doesn't scale so well. I think a number of years ago, it would scale to like 30 alternatives. Maybe now the solvers have gotten a little bit better. But it turns out with the graduate admissions data, it actually easily scales to 150 applicants just because the input rankings tend to so much agree with each other already, right? We tend to actually agree, not always, but for the most part, which candidates are better than which other ones. Okay, good. And here's another, this is basically the same integer program, but with some things done a little bit differently. If you're interested, you can go home and figure out why they're the same thing. Okay, some references. So finally, a couple of words on Dodgson. I'm not going to get into the technical details of that. But this one is also NP hard to compute. And one interesting direction is that people have said, well, let's try to, in fact, get an approximately optimal Dodgson score, right? Because Dodgson is also an optimization problem. We try to make some alternative to Condorcet winner with as few swaps as possible. So let's try to get something that always gives us an approximate winner. An interesting thing is that when you do something approximately, and actually also people have come up with approximate versions of Kemeny, but if you do something approximately, you're actually going to get a different rule, right? And so some of the properties that you might have liked about the original rule might be gone. You might actually get new properties, and maybe you like those, right? So that's one point. Okay, but that's all I'm going to say about rules that are hard to compute. So any questions about that? Good. Now I want to talk a little bit about manipulation, and particularly this idea of using computational hardness as a barrier against manipulation. So this is a topic that's gotten a lot of attention in the computational social choice community, this idea of if we can make manipulation computationally hard, that might actually be beneficial from a mechanism design point of view. Right? So instead of making it impossible, we try to still leave it possible because we have things like the Gilbert-Satterthwaite result, but we try to make it really hard. Okay, so remember the Gilbert-Satterthwaite result, we talked about it yesterday. It says that if there are no restrictions on the preferences and we have at least 3 alternatives, then if you want something that's strategy proof, it's going to have to either be dictatorial or it's going to have to exclude some of the alternatives even before the votes come in, right? In fact, all but 2 of the alternatives. Now, one way around this is to make some assumptions about the preferences. So you've already seen a lot at this school about quasi-linear preferences. If people can make payments and transfer utility to each other, then you can get around a lot of this. I want to just mention the case of single peak preferences, which many of you may know. This works as follows. So suppose that we have the following restriction on preferences. Suppose that the alternatives are ordered on a line from left to right. And it doesn't have to be a line, but they're ordered. For example, you might have your left-wing political candidates. This one is a little bit closer to the center. This one is centrist. Here you have a very right-wing political candidate. That's one thing. It doesn't have to be political candidates. You might be voting over something like the tax rate, right? And so then very naturally you would have lower tax rates and higher tax rates. Of course, every voter is going to have a most preferred alternative. We're going to assume that every voter prefers alternatives that are closer to her most preferred alternative than ones that are further away. Okay? And to be a little bit more specific, that means that if your most preferred alternative is A3, then you must prefer A2 to A1. And actually the condition is just on each side, right? So you might actually, even if your most preferred alternative is A3, it's allowed that you actually prefer A5 to A2 because they're on different sides, but you can't possibly prefer A5 to A4, right? Skipping over something. Does that make sense? Right? Then what you can do is you can say, okay, suppose that you only prefer you only report your most preferred alternative. So here we have some voters that have different most preferred alternatives. Then what we're going to do is we're going to take the median voter. Okay, the median voter is the voter that's right in the middle, right? So this voter in this case, right, has 2 voters are to the left of it, 2 voters are to the right of it. This is the median voter. And we pick that voter's most preferred alternative to be the winner. first thing to point out is, and so let's assume that there's an odd number of voters, so we actually have a median. Otherwise, you have to think about whether you pick the left or the right median. First of all, this is going to be the Condorcet winner. Can somebody see why? Remember, the Condorcet winner is one that defeats every other alternative in pairwise elections. Can somebody see why this is the case? Yeah.
Well, if you drew out the graph that we had on the board
Uh-huh.
yesterday, it would be impossible to have any cycles.
That's true. But why?
Because everyone has a strict ordering over their preferences.
Right. So it is true, but sorry.
If you take any candidate left to the median,
Uh-huh.
then all the voters at the median and to the right of the median, which are more than half, prefer the median to that candidate.
Exactly. So that's a simple argument, right? So if you look at, for instance, let's compare A1 and A2. Here, A2 is the peak of the median voter. So all of the voters on the right, by the assumption of single peak preferences, will prefer A2 to A1, right? That's the assumption of single peak preferences. And of course, also the median voter will prefer it. And we know that at least half of the voters are to the right, and we have the median, so more voters will prefer A2 to A1, right? So that's how you can see it's the Condorcet winner. Also, this is strategy proof. There's no way to manipulate this, right? That's also not that hard to see. If you are the median voter, you're as happy as can be, right? So there's no reason for you to manipulate in that case. Let's say you're not the median voter, like maybe you're V1, right? How can you change the outcome? If you move your vote somewhere to the right, so somewhere that's still to the right of A2, you're not going to change the outcome, right? We wouldn't change where the median is. You could change the outcome by jumping all the way to the left, right? But if you did that, you would just be making the outcome worse for yourself. You'd be pushing the winning alternative away from yourself. So that doesn't help. So that's why it's strategy proof. And actually, you can see it's group strategy proof. There's no coalition of voters that could all band together and get a better outcome for all of them. Okay. So the key point is that if you have some restriction on the preference space, these impossibility results might go away. Okay, I want to briefly talk about this idea of using computational hardness as a barrier to manipulation, right? Because what Gilbert-Satterthwaite tells you is that you can't avoid the existence of some opportunities for manipulation, but maybe if they're hard to find, they wouldn't happen, and so we can actually avoid them that way. This is an idea that's gotten a lot of attention, and it goes back all the way to so the simplest version of the problem considers the case where you're a voter. Somehow you already know what everybody else is going to vote or has voted. Okay? So you know all the votes of the other voters. You have some alternative P that you would like to see win the election. And you know what the rule is. And you're asked, well, can you cast your vote so that P wins? Okay? So here's an example. So suppose you're in this situation, you're voter 4, you see that the votes of 1, 2, 3 are like this, giving you the current Borda scores as follows. And you're asked, is there some vote that makes B win? Is there? So how would you vote to make B win? BCA, right? That's going to do it. If you vote BCA, you're going to give B 2 extra points. A is not going to get any extra points, and C is going to get 1 extra point. That's okay. B will still be ahead. Okay. Now you can imagine. So for Borda, this problem turns out to be easy, but for some voting rules, it turns out to be hard. The first rule for which it was shown to be hard is actually kind of second order. So this is here you measure how good an alternative is, not by its Copeland score, but by the sum of the Copeland scores of the alternatives defeated by this alternative. Okay, there it turns out to be hard. A better known rule is actually STV. So later it was shown that for STV, this problem is NP hard. almost all other rules that we care about, well, we'll see in more detail. Also actually ranked pairs. Remember ranked pairs? You take this pairwise selection, a majority graph, and you lock in the edges with the greatest weight first. So we first lock in this edge, it's the biggest, then this one, then this one, then this one. Now the next one would be B to C, but if we actually lock that in, we would get a cycle A, B, C. So we can't lock that in. We actually have to go the other way because it's already implied by the cycle or by preventing the cycle. And then finally, the same is true over here. Here also it turns out to be NP hard to manipulate. And in fact, a lot of research has gone into figuring out exactly which ones are NP hard to manipulate and which ones not. Most of them turn out to be easy to manipulate. The only exceptions are STV, rank pairs, well there's these second order coupling things. Nansen and Baldwin are kind of analogous to STV but using it on Borda in two slightly different ways. You could also consider the problem of multiple manipulators working together to change the outcome. Then a couple more become hard. Okay, so this is nice, and so the first reaction that people had was, well, this might be a really promising approach. There is, however, a problem, which is that NP hardness is a worst case notion of hardness, right? So that means that if a problem is hard, it's unlikely that you're going to find an algorithm that scales well on all instances. But it doesn't mean that you can't find an algorithm that does well a lot of the time. Also, all of these results actually require that the number of alternatives gets quite large, right? Because in the reduction, the number of alternatives blows up. So just as an example, right? So let's focus on STV for a second. I'll show you a very simple algorithm for manipulating STV optimally that makes, it's a recursive algorithm. The number of calls is 1.62 to the m, where m is the number of alternatives. If you think about it, that's, for most elections, that's not going to be that large of a number, right? Even if you have 20 alternatives, you're going to have 15,500 calls, right? But it's a pretty reasonable number. Okay, and sometimes you really have a larger alternative space, right? If you're really voting over joint plans and you have some kind of combinatorial space of plans, then that might be an issue. In California, a lot of people get to run for governor, so maybe that's another example. But generally, maybe not. Okay, so here's the algorithm. Actually, it's not that complicated, right? So if you imagine for a second, so you're in the situation that everybody else has already voted, or somehow you know everybody else's vote, you're still casting your vote, right? You can think about how the election would proceed without your vote, and how you could change it, right? So you look at the first round, and you say, okay, well, if I didn't do anything, if I didn't vote, D would get eliminated, right? Now, there's two possibilities. Either there's nothing you can do and D will get eliminated at this stage, even if you were to vote for D. Or you might be able to save D, right? If you might be able to put your D in your first position and then D does not get eliminated. That's another possibility. And I'm assuming that you have some kind of deterministic tie-breaking rule here. Interesting thing is that if you rescue D, right, then something else gets eliminated, let's call it C. The next round, you have no choice in what happens anymore, right? Because your vote at this point is committed to D. It won't be able to transfer because by assumption you've rescued D, right? So something else will get eliminated. Maybe it's B. That means that you still don't get to change what happens in the next round. Maybe the next round D still will get eliminated. And then the next time you might have a choice again, right? Because whatever you put second, that's where your vote is going to transfer. And that with that, maybe you're able to rescue the alternative that would have been eliminated next. Okay. On the right-hand side, you didn't rescue D, so your vote is uncommitted. So you can maybe choose to rescue the next alternative or not. If you did rescue it, then your vote is committed at that point, right? And so that's how it proceeds. Does the algorithm intuitively make sense? Okay. So the running time of the algorithm you can analyze like this. So if the number of recursive calls as a function of the number of alternatives is T of m, also let's think about T primed of m, which is the number of calls given that your vote is currently committed to some alternative, like the alternative that you just rescued. Then you get the following recurrence relation, which is that if your vote is currently not committed, well, so you'll have this call, and then you'll go to a number, you'll go to the next stage where if you were able to change something at all, if you weren't able to change something, then you'd just be back at t of m minus 1. But if you had a choice between rescuing an alternative and not rescuing it, then you have a branch in the tree. If you were able to rescue it, then that branch corresponds to t prime m minus 1, because now you have one fewer alternative, but your vote is committed. And over here, you chose not to rescue it, so you still have the freedom. You might be able to branch the next round. If your vote is currently committed, then you're going to have this call. It's possible that your vote the next round is no longer committed, and then you're back at t of m minus 1. Okay? So if you solve this, you're going to get that solution that I just told you about, 1.62 to the m. Now, I think really, so you know, it's, first of all, that exponential doesn't scale too badly when you're talking about typical elections, but maybe the more notable point is that this analysis assumes the worst case, right? The worst case would be that every round you actually have a chance to save somebody unless your vote is currently committed. And usually that's just not going to be the case, right? Usually it will be quite rare that you have the opportunity to change the outcome of a round. It might happen a couple of times in the tree, but not very often, right? And then you have a much, much smaller tree. And so Toby Walsh actually used a version of this algorithm and showed that in experiments, this is really effective at manipulating elections, right? Simulated elections. Okay, so I'm going to skip over some stuff here. Right, and so this is this point of the worst case nature of NP hardness results, right? It says there are going to be some instances that are really hard, but that may not be very satisfying. If most instances are easy to manipulate, we haven't really achieved that much, right? So that leads to the question, is there some way of making most manipulable instances hard to solve? So a lot of work has now gone into showing that that's not the case. It's not really possible to do so from a lot of different directions. And so I think this approach is kind of, this approach of making voting rules hard to manipulate, it's kind of lying in its coffin right now, and people are hammering nails into it. Maybe there's still like a little way out of it, but it's not looking good. So one direction is just these heuristic algorithms, right? Just by simulation, let's try to figure out how easy it is to manipulate randomly generated instances. Sometimes with a little bit of theory mixed in as well. There's some nice work that shows that, and this is more formal work, where you can show that, well, if only you have a few more manipulators, you will be able to easily figure out who wins, or whether you can manipulate the election. Another nice direction is showing that really what makes manipulators able to manipulate an election or not really depends on their number, right? If you're thinking about a coalition of manipulators, it turns out that, well, at least if you assume that all the other voters are drawn IID, or at least independently of each other, then really what matters is whether the number of manipulators that you have on top of that is more or less than the square root of the number of non-manipulators, right? If it's less, then with high probability you won't be able to change anything. If it's more, then with high probability you will be able to make every alternative the winner. Well, unless it could be that the manipulators, right? So if the manipulators were drawing uniformly at random, then you would be able to make every alternative the winner. If the non-manipulators are systematically biased against some alternative, you'll never be able to make that alternative the winner. But as long as the non-manipulators are unbiased between two alternatives, then, and there's more than root of n manipulators, then they can make either of those alternatives to win. And then maybe the technically nicest stream of work is actually to prove quantitative versions of Gilbert-Sudduth-Waite. And I think somebody in the audience has actually worked on this. And so here the idea is, so the Gilbert-Sutherland weight just tells you that if you want no chance of manipulation anywhere, you're going to have to give up either on non-imposition, so that some alternative will never have a possibility of winning, or on non-dictatoriality. And what these results show is a quantitative version of that, which is saying that if you're kind of far enough away from having a dictatorial rule and far enough away from having an imposing rule, then if you pick a random profile and for one of the votes you randomly permute it, you have a good chance of actually manipulating the election to your advantage. Okay? And so that suggests that given a rule, you can find an instance that is manipulable quite quickly. Good.
What's,
Yes?
in your opinion, the most convincing argument that these are really bad things? I mean, why do you think it's bad that voters can, in general, manipulate?
Why is it bad that voters can manipulate?
You don't even know what's a good outcome, right? Otherwise, you can have all these like 50 or 60 or 100 different voting groups.
Oh, I see.
Why is it worse now when people are manipulating?
So I think, one reason is the revelation principle. There's some caveats with that, right? But so in mechanism design theory, there's the revelation principle, which says that if you can achieve some outcome with strategic agents, you can effectively achieve that same outcome with a truthful mechanism. Now you have to be a little bit careful there, because what truthful means depends on the solution concept you were using, right? So if you have something, a good outcome in Bayes-Nash equilibrium, that means that there's a Bayes-Nash incentive compatible mechanism that will do that well.
Mechanism design, we have some well-defined goals that we're trying.
That's true.
Like revenue. Okay, so I know what's good. It's good that I earn more money. Okay, but
Right. So one thing with voting is you don't have a quantitative objective. So actually, I think the next result that I'm going to show will address that maybe to some extent. Right. So let me skip this. So let's think for a second about, this is something else, but let's for a second think about doing something like a price of anarchy type of result, right? Like maybe you can somehow show that even though you're always going to get some manipulation, at least in some cases, you can prove that any equilibrium will still have a reasonably good outcome in some sense as compared to the optimal outcome. Again, it's tricky because
maybe the truthful outcome does not have these properties, but the equilibrium that you mentioned does have these properties.
which property?
The good properties.
Yes.
You haven't defined it.
So we'll get to that in a second, right? Okay, but so let's think about how might you prove a price of anarchy type of result? If you think about simultaneous voting, there's a little bit of a problem, right? So let's look at these preferences. So the true preferences are in their thought bubbles. By the way, so normally Lirong stuns me with his deep technical insights. This time he stunned me with who he chose to make the voters. So here the voters are Superman, Spider-Man, and Iron Man. I guess it makes sense because I think they're all U.S. citizens. So that's maybe okay. So in this example, actually all of the voters in their true preferences, they put McCain first, right? But for some reason, they're all expecting each other to vote for Obama, and as a result, they might as well vote for Obama as well because they can't make any difference. Okay? It's kind of a very strange equilibrium, a very non-obvious one. But if nobody really likes Obama, it's a bad equilibrium, right? If that really were the case, right? This seems maybe a little bit silly. How would you ever get to that kind of situation? But what maybe looks more realistic is that you could have a situation where everybody really likes Nader, right? But nobody is expecting Nader to win, and as a result, they all vote for the other two alternatives, right? And so you're in a bad equilibrium just because of people's expectations. And so with this, you can easily come up with examples where everything looks very bad, right? You can look at the bottom two alternatives, like you could have two alternatives be the bottom two alternatives for everybody, and still everybody is voting for those two alternatives because somehow they're expected to win, and if everybody else is voting for those two alternatives, you better do the same. Okay, so that kind of suggests that there are just kind of too many equilibria in simultaneous voting. Yes?
I once heard the advice that in polls you should choose the candidate that you really prefer rather than the one so that they would vote for him. But it just occurred to me now, would this kind of poll also be strategically manipulable?
Right. So that's, I guess that's the issue, right? Right, so you would have to think about your incentives in that poll as well, and in general, those won't necessarily, right? Because you might imagine, like, a simple thing to imagine is there's a fourth candidate. You really like this fourth candidate, but you think that if you don't put enough, if you don't vote for the third candidate, let's say Nader, in the poll, right, then Nader's not going to get enough attention, so now you're being strategic in this poll already. It's an interesting question of, like, can you change, maybe by having enough polls or something, can you change the equilibrium? I'm not sure.
Andrews has, I think, spectrum of that.
What's that?
I think Andrews has
He does?
pictures of that.
Okay.
Polls, like strategic polling.
Okay, cool. Nice. And what is the result? Okay.
People do, they can strategize polls. They can, it makes sense to strategize.
Right. And of course, I mean, at the end, there's always going to be Gilbert-Sutherthwaite hiding again somewhere, right? You can't get around that. Okay. So what we looked at instead was what we called Stackelberg voting games, where the voters vote in sequence as opposed to voting all at the same time. Okay. And so the sequence is common knowledge. And we're going to assume kind of a very complete information setting that when it's your turn to vote, right? So imagine that all the voters are sitting along a table and we're going clockwise around the table and everybody's casting their vote in order. So you hear what everybody else has voted so far. You know very clearly what the order of the voters is going to be. We're also going to assume, and this will actually just make the results stronger, that the preferences are common knowledge, right? So you're voting with some people that you know so well that you already know what their true preferences are. But you know they're going to vote strategically as well. And finally, you also know the rule that's going to be used to select the winner. If you think about it for a little while, in subgame perfect Nash equilibrium of this, right, you can use subgame perfect Nash equilibrium because it's a complete information game. There's going to be a unique winner, right? Because you can always figure out what the very last voter will do. Right. I'm assuming, by the way, that everybody has strict preferences over the alternatives, right? So you can always figure out in every situation that you might put the last voter, you would know what the last voter would do. Then the second to last voter, whatever situation she is in, she can anticipate what her actions would make the very last voter do, and so you can go all the way back to the beginning. And you won't quite get a unique subgame perfect equilibrium because you might have two different votes that both get you the same result. But the winner will be unique in subgame perfect Nash equilibrium. And so could you get kind of bad outcomes in this situation? So here's an example where you get a bad outcome, at least relative to the preferences that are here. So suppose that we use plurality rule, but we have a tie-breaking mechanism according to this order, right? So if two alternatives are tied, ties will be broken according to this order. And Superman gets to vote first. Iron Man gets to vote second. What's going to happen? And so we draw the game tree. So let's say that Superman votes for McCain. Iron Man then... so what can Iron Man do? Iron Man can make Clinton win, right? Because... So really, Iron Man can always make Clinton win as long as Superman does not vote for Obama. Does that make sense? Right? Because if Superman votes for any of the alternatives down here, then by voting for Clinton, Iron Man will make Clinton win because Clinton will be tied with this other alternative, and the tie is broken in favor of Clinton. Okay? So and of course, Clinton is Iron Man's most preferred alternative. But unfortunately for Superman, that's his least preferred alternative, right? The only way he can prevent it is by voting for Obama, because ties get broken in favor of Obama. By voting for Obama, he will immediately guarantee that Obama wins, right? Because all ties are broken in favor of Obama in this particular version. So in subgame perfect equilibrium, Obama wins this election, right? But in this case, actually, that's quite bad for the preferences because Obama is close to the bottom for both of them, right? So this is kind of an example where you have a high sort of price of anarchy, right? Or also called the paradox. So you might wonder, well, this might just be due to plurality, or maybe not even just due to plurality, but due to this weird tie-breaking mechanism, and maybe it doesn't always occur. It turns out, unfortunately, that you can have a very general result that shows that there are, in fact, instances where the subgame perfect equilibrium outcome is bad, right? So this is actually only a special case of the theorem, but if you look at voting rules that satisfy the majority criterion, remember that's where if more than half of the voters rank the same alternative first, that alternative wins. So a lot of rules satisfy that. Then there exists a profile such that this here is the winner that you would get in the subgame perfect equilibrium. In all but 2 of the voters, that alternative is ranked in the bottom 2 positions. And also the winner loses in pairwise selections to all but 1 alternative, right? So going back to Reshev's question, so how do you really evaluate how good your outcome is, right? And that's not so clear, and a lot of social choice is precisely about, well, what rules are more reasonable, what are the outcomes that we even really want. But I think it's pretty clear you don't want this outcome, right? No matter what your criterion is going to be, this is going to look bad. So in the worst case, this kind of strategic behavior can be really harmful. Interesting thing is that if you simulate it and you draw lots of random preference profiles and you see how well they do, in some sense actually the strategic winner does quite well. So here, this is the result of a bunch of simulations. On the left-hand side, what we see is the percentage of people who prefer the strategic winner to the truthful winner, if everybody had voted truthfully, versus minus the other way around. So if this is above 0, then there is a sense in which the strategic winner is actually doing better, right? Or at least as compared to the non-strategic winner, more voters prefer the strategic winner, which is kind of interesting. And so I don't really have a good general or theoretical explanation for why this happens, but it seems to happen in experiments. Good. So that's it for strategic voting. Any questions about this? Good. Okay, good. So another topic that I think is interesting is how much communication actually needs to take place to determine the winner of the voting rule. So far we've assumed that all the voters just report all their preferences all at once. You can imagine that in an election with a lot of different alternatives, this actually gets to be kind of a pain to do. First of all, maybe from an actual communication standpoint, you have to fill in a lot of information. But especially from just a cognitive viewpoint, right? You actually have to decide for every pair of alternatives which one you like better. Is it really necessary, right? Or might you really be wasting your time on some of these candidates, right? Can we maybe save you the effort of figuring out which of 2 alternatives you prefer if neither of those alternatives has any shot of winning? Or even if one of them has no shot of winning, right? That would seem to make sense. And in general, we try to limit the number of participants or the number of alternatives in an election, partially probably for that reason. So the general model of preference elicitation goes something like this, right? So you can imagine that instead of having everybody report their votes all at once, we have a central agency that repeatedly queries voters for different aspects of their preferences, right? So this organizer might ask the first voter whether he prefers McCain to Nader, and the first voter says yes. Based on that, maybe the center goes back to this other voter and asks whether he prefers Obama to McCain. No, and maybe a different kind of query to the third voter, which one does she prefer the most, and she says McCain, and goes back to the second voter and another query, right? And finally, at some point, the system decides that a particular alternative has won, right? And so you can imagine that this way we could maybe save a lot of communication, and maybe you can actually come up with the same winner, right? So if, depending on what your algorithm is here, you might actually have a guarantee that you're always going to end up with, for instance, the Borda winner. Right. By the way, we're assuming here that voters are completely non-strategic again, Right? If voters are strategic, you have to worry a lot about what the queries might reveal, about what other voters have voted, and so on. It gets very complicated, so we're just ignoring that at this point. So we're going to suppose that everybody always answers truthfully. And so now what you can do is you can say, okay, for a given rule, what is a natural algorithm for asking queries to the agents voting to minimize the number of queries, or really to minimize the amount of information? So just as an example, let's think about the single transferable vote rule, right? So here, what we've assumed before is you rank all your alternatives and then the system automatically figures out how they transfer, right? If we try to elicit less information from the voters, how might you do it, right? But you can kind of repeatedly go back to voters and ask them new queries. What is a natural way for the STV algorithm to do this, right? Remember the STV algorithm, we look for the alternative that is ranked first the least often. That one drops. If you were one of the few voters that actually put that alternative first, your vote now transfers to the next alternative on your list. We recalculate everybody's score. Again, the one with the lowest number of votes drops out, and so on. So what is a natural algorithm for asking queries to the agent so that we have less communication? Right? And the idea here is that if your preferences way at the bottom might really not matter because you might never get there. Kristen? Yeah, so you might start by asking, well, who do you rank first? What would you do next? Okay, so let's even just say that we do it for everybody just to keep it simple, right? So we ask everybody who they rank first. You're right that we might not even need to. We might be able to stop early, but we're going to be interested in the asymptotics of the worst case, so it won't actually matter. But okay, and so then once we know, then we figure out which alternative drops out, right? So what do we do then? Yeah, so that alternative will be ranked at the bottom of our aggregate ranking. But
then you're going to have a new person at the bottom according to what you currently know?
Yeah, usually we think of the top, right? The top of the vote is maybe where your most preferred alternatives are. Right, but so if you were one of the few people that actually did vote for this alternative that got removed, you ask those people again, right? Say, well, what is your most preferred alternative now that we've removed this one, right? That's a very natural algorithm for STV, and that turns out to be the best one that we know asymptotically. Bucklin is another. This one gets a little bit more interesting. So remember, Bucklin, we look if there's some alternative that's ranked first by more than half the voters. If so, that one wins. If not, then we look at the first two positions of everybody's vote. And if there's some alternative that's ranked in those first two positions by more than half the voters, that one wins. Otherwise, we go to the third and so on, right? So what's a natural algorithm there? So it turns out to get the optimal asymptotic complexity, this one is a little bit trickier, but what is a natural algorithm? Pretty much the same, right? So you could do this. You just ask everybody for their top alternative, see if there's somebody there that gets named more than half the time. If not, then we ask everybody for their second ranked alternative and so on. Turns out asymptotically this is going to be up to a constant factor, just about as bad as just asking everybody for their complete preferences in the worst case. Because it could be that you have to go pretty much like halfway into their votes before you find the winner. Okay, and so maybe you've saved a factor of 2 now, but that's not very significant. Does anyone see an idea to do better? And really the crucial thing in some sense is to find this point k, the first point at which you have some alternative that gets ranked in the top k by more than half the voters. Yes?
Like binary kind of double,
Yeah.
that kind of search.
Exactly. So we do a binary search for this magic number k where somebody goes across the threshold of having more than half the voters. And so how do you do the binary search exactly?
Start from 1, keep doubling, and whenever you exit that, then...
Mm-hmm. Good. So this is how you do it. Here's a concrete example. So the first thing, here we happen to have 8 alternatives, right? So let's say we start in the middle and we ask everybody for their top 4 alternatives. And the key thing now is that they don't have to rank their top 4 alternatives, right? If they have to rank them, then we're getting too much information. We just want to know which they are. Okay, so once you see these answers in this particular example, we see that A is named by more than half the people, but so is B. So we don't know, this is, we might have overshot, right? It might be that B is among the top 3 for more than half the voters, and A is not, right? So here we've overshot potentially, and so we want to look for a smaller set of positions. So we ask for the top 2, and we get maybe this answer. And so we see now in the top 2, no alternative appears twice, right? So no alternative gets more than half the vote. So now we went too far in that direction, so we ask for the top 3. And now we see that there is exactly one alternative left, which happens to be C, that gets named twice. So C wins. Okay. Now you have to be a little bit careful in analyzing this. So how many bits of information does this round take? Or an upper bound? Well, so clearly it takes at most m bits, right? Where m is the number of alternatives. For every alternative, you have to say whether it's in the top 4 or not. It's actually less than that, right? But that will be enough. Now, when you go over here, actually, you only need m over 2 bits now, even less than that, right? But because you already know, the center already knows that these are the top 4 alternatives for this voter. It doesn't really need to, when it's asking about the top 2, obviously it knows that the remaining alternatives, E, F, G, H, they're not going to be in the top 2 because they're not even in the top 4, right? So here there's only 4 alternatives for which a bit needs to be communicated. Then when you go to the top 3, you know that it's got to have to be either B or C. Sorry, yeah, B or C, right? So now there's only 2 bits, and so if you add it all up, what you're going to get is 2 times n the number of voters times m the number of alternatives. And so it turns out that that's actually asymptotically the best you can do here as well. Okay? And then you can study this for a lot of different voting rules. For some voting rules, you can actually prove a lower bound that says that you can't do better than, no more than a constant factor, better in the worst case than having everybody communicate everything, right? N times m log m is the total amount of information that you would need to communicate to get your whole ranking across. And so for some rules, you just can't do any better, but some rules actually save you a lot in terms of communication. Even STV does not take that much, but actually there's still a little bit of a gap for STV. And then there's some interesting work recently on the communication complexity of finding an approximately optimal winner in voting. Okay, so that was that for communication complexity. And by the way, a good thing to keep in mind is all of these techniques and approaches might also find application in a lot of other types of domains, other social choice domains that are not necessarily voting, right? So as a graduate student especially, it's good to think about, when you see somebody applying a technique, where else can you apply that technique, right? Or if you have a technique that you're familiar with, how can you apply it to some new domain that you see? So that's good to keep in mind. Last thing I want to talk about is what I think might be the most exciting direction in social choice is this notion of combinatorial alternative spaces. So far we've just assumed that we can list and rank all of the different alternatives, but in some contexts, actually the space of alternatives that we get to choose among is itself exponential in size. So you couldn't rank everything. So here's a kind of playful example. So suppose that we have to decide on both a dish for dinner and the wine to drink with the dinner, right? So the dish could be either fish or meat. Sorry, I should have included a vegetarian option as well. But the wine can be either white or red. And so this gives you 4 different combinations, right? More generally, you're going to have some set of issues on which you have to make a decision, like the meal and the wine. For each issue, there's going to be a domain of values that you can draw from. And then the total alternative space is the Cartesian product of all of those different domains for the different issues. Right? Does that make sense? And so here, the number of alternatives is going to be exponential in the number of issues. Here it's only 2 issues, but in general you might get more issues. Right. And you can imagine this leading to systems of government where voters could be voting more directly over the issues instead of on representatives, right? This is kind of a problem that we face, right? Or maybe right, in a system of government, you might have everybody having to vote for or against the bill, whereas really they want to express their preferences in much more detail, that they say, well, this section of the bill is nonsense, it shouldn't be there, and this other section I think is really good, right? But typically, with our current systems, we're not able to have people express those kinds of preferences. So, for example, you might have a general plan that has a transportation component, an environment component, and a plan for building a hospital. And so you want to be able to vote on this, and there might be relationships between those things as well, right? What your preferences are on the environment issue might depend on what the plans are for the transportation issue, right? If a particular highway gets built, you might want to build a bridge for wildlife, for instance. And maybe also whether you want the hospital built might depend on the transportation plan as well, because it depends on that. It depends whether people are able to get to the hospital or not. Okay, so how do you even have voters naturally represent their preferences in a context like this, right? You could have them vote separately on the different issues, but that might get very tricky because of these dependencies, right? You're maybe not able to state what your preferences for the hospital would be until you already know what the outcome is for transportation. So in the AI literature, there's a couple of different ones, but here's one scheme that gets used a lot. This is this notion of a CP net. In a CP net, again, we're in a similar kind of environment where we have some set of variables on which we have to make a decision, each of which has to take a value from some domain. Your preferences are going to be represented, A, by a directed graph, where the nodes of this directed graph are the different issues. And so these edges tell you for which issues your preferences depend on other issues and on which other issues they depend. And then additionally, for every issue, you will have a conditional preference table that tells you what your preferences for that issue are given the value of the parent issues, right? So the issues that have an edge pointing to it. So this should, if you know about Bayesian networks, it should look very similar to that. So here's a concrete example. We have x, y, z. Both of them are binary variables. And here's the graph. So your preferences for x depend on nothing. Your preferences on y over y depend on x, and your preferences over z depend on x and y, right? Two edges, right? And so for x, you just generally prefer x and not x. For y, if x is true, then you prefer y to not y, and if x is false, you prefer not y to y for some reason. Right? And then for z, it gets more complicated because you have to think about every single combination. Okay. Interesting thing to notice that in general, this won't imply a full order over all the alternatives. You'll just get a partial order out of this. Right? So for example, here, if you look at this voter, does this voter prefer XYZ or X not YZ? We can look it up simply because the only difference is in Y. We can go to that table and see, well, given that x is true, y is preferred to not y, right? So that's why we get this edge, right? And then by transitivity, you can get a lot more relations as well. But it turns out, in this example, there's no way to figure out whether the voter prefers x not yz or x y not z, right? There's no table in which you can look that up because it differs on two different issues, right? So a table only tells you if you flip one issue, which of the two resulting alternatives would you prefer? But if there's two different ones, you might be able to figure it out from transitivity, but you might not. And in this example, you're not. Okay. So a lot of work has focused on how do you now take these CP nets and aggregate them into a sensible winner. I'm only going to talk about maybe the simplest approach, which is sequential voting rules. One thing to point out, by the way, is that this graph here is acyclic, right? And if you know about Bayes nets, you might immediately conclude that, well, yes, Bayes nets are always acyclic as well. But here, actually, it does make sense to have cycles, right? You might actually have an edge pointing back into x, that if you flip x, given that y is set to false, you might actually have a different preference for that as opposed to when y is true. Okay, so cyclic CP nets actually do make sense. That being said, let's restrict for a second to acyclic ones. Okay. So again, we have our set of issues and the domains in which they take values. Now also assume that there's some order over the issues, okay, and that every voter's preferences are consistent with that order in the sense that your preferences for later issues only depend on earlier issues. Okay, so it's never the case that you have an issue for which the preferences that you have depend on an issue that's later in the order. Okay, and that's an assumption, and it does rule out some preferences. But if you have that situation, one thing you can do is you can say, okay, for every issue individually, we're going to have some voting rule, and we're just going to go through the issues one by one, right? Because your preferences only depend on earlier issues, when you're then made to vote on a particular issue, you know what your preferences for that issue are because you already know what the outcome on the earlier issue was. Okay, this is this notion of sequential voting. So for example, here, you might have, again, our example of choosing over a main dish and wine. And now let's assume that your preference for the main dish is unconditional of the wine. So then first you vote on the dish. And so here it happens that 2 voters prefer fish to meat. So we're going to go with fish. Then the next thing we vote over is wine. So this part here becomes irrelevant because those would be your preferences for wine, given that meat has been selected, but meat has not been selected. Fish has been selected. And so it turns out more voters prefer white wine to red wine with fish. Okay? So that's this idea. Again, this notion of acyclic CP nets is restrictive, so there is some study of how you generalize this to settings where the preferences, where the CP nets are cyclic, but we're going to skip over that. And actually, now I want to move on to thinking about strategy again, right? Strategic voting. So, what might happen if voters vote strategically in such an election, right? An interesting aspect of that is that, so let's go back to this example. Suppose that your preferences for fish actually or preferences for the meal actually did depend on which wine was selected, right? Then there's no sense in which you can vote honestly here anymore, right? You're asked what your preferences for the meal are, but you say, well, I really first need to know what the wine is to be able to decide which meal I prefer. Right? So truthful voting kind of it becomes meaningless. It's not really clear what truthful voting means anymore. But strategic voting actually still makes sense. Okay, so if you consider this situation where, just to keep things simple, let's think about binary issues like we've done so far. Every variable has to take a yes or no answer. And it's going to take a little bit of a similar flavor to the Stackelberg voting that I told you about, except here, instead of the voters voting in sequence, we're going to have all the voters voting at the same time, but we're going to vote on issues sequentially, right? Just like this sequential voting. And for each issue, we'll use majority rule to decide what value to give that issue. The nice thing is now you can, again, get this kind of backward induction solution, because when you're voting for the very last issue, right, because there are only 2 values for that issue, you're going to have a clear preference at that point, for one value or the other for that issue, because you know what all the other issues have as their values at that point. And in majority rule, you have a dominant strategy of telling the truth when there's only 2 issues, right? And when there's only 2 values. So you can predict what would happen in the last round. Now you can go one round earlier, right? So think about the second to last round. So we have to decide on some issue there. It has to take a value, either yes or no. And because we're assuming that we have complete information, everybody knows everybody's preferences again, everybody can predict, depending on the outcome of the second to last issue, what will happen with the very last issue, right? It might depend on what value we give the second to last issue, but everybody can predict what it would be, right? And so effectively, everybody is choosing between 2 alternatives at that point. So let's look at it more concretely. So suppose that so now the 2 issues are, do we build a swimming pool or not? And do we build a tennis court or not? right? And again, your preferences might be interrelated. You might say that, well, they really go very well together because after tennis I want to take a swim. Or you might actually say that they're substitutes, right? I don't have time to do both, but I want to be able to do some kind of sport, right? So here you have the different preferences of the voters. Voter 1 prefers to have both built. Next most preferred alternative is just a tennis court. Next most is just a swimming pool, and least preferred is to build nothing, and so on. Okay. And again, we're going to use sequential voting. So we're first going to vote on whether the swimming pool is built. Then next we're going to vote on whether the tennis court is built. Okay, and so let's first think about the case that, suppose that in the first round we had selected the swimming pool to be built. Then what would everybody's preferences be? Well, voter 1's preferences, given that a swimming pool has already been built, she would still like a tennis court to be built as well, right? ST is preferred to S not T. Voter 2 would prefer a tennis court not to be built, and voter 3 also would prefer it not to be built, right? So if we get to the stage where a swimming pool has been decided to be built, then we're going to end up with just a swimming pool. On the other hand, we can consider the case where in the first stage we have not built the swimming pool. And in that case, this voter and this voter will prefer a tennis court to, actually all of them will prefer a tennis court to be built. Okay? So in that case, we actually get the outcome that only a tennis court is built. So everybody realizing this in the first round, they realize that really what they're making a decision on is not just the swimming pool, but implicitly also the tennis court, right? If you're going to get the swimming pool to be built, then in the next round the tennis court won't be built. And if you don't get it built, then in the next round the tennis court will be built. So that's what they're going to be deciding between in the first round, implicitly. And you see actually 2 voters prefer the outcome where there's just a tennis court and no swimming pool. So they will vote against the swimming pool so that the tennis court will be built, and this will be your final winner. Right? Does this process make sense? And so this, in some sense, always works, right? You can always, at least theoretically, figure out what the winner is going to be. And now we can ask this kind of price of anarchy question again. Can this lead to bad outcomes? Unfortunately, it turns out that it can. Really, there's a collection of results behind this. But roughly what it says is, given enough voters, you're going to be able to construct some profile so that the strategic winner, right, that the outcome that happens with strategic voting according to what we just saw, is going to be ranked almost at the bottom in every vote. Okay, so that's certainly not good. And it's going to be Pareto dominated by almost every other alternative, almost Condorcet loser, right? So again, this shows that strategic voting can lead to bad outcomes. There is actually literature on what's known as multiple election paradoxes, which is also this idea of if you're voting on multiple issues at the same time, you might actually get an outcome that doesn't reflect the preferences very well, right? But some of those results use kind of non-strategic, but some kind of assumptions on how people will actually vote. I like this result because it's just pure strategic voting. So we have those 2 different results. Actually, one thing I forgot to mention with the first one, the Stackelberg result, that there too we had this result that strategic voting can lead to very bad outcomes. One interesting question there also is actually how hard is it to compute what the strategic outcome is? We think this is probably a p-space complete problem, but it's hard to prove. And there are some tricks for some rules that you can do to speed up the computation a little bit, which is why we could still have some simulations. But I think there's some interesting questions there as well. All right, just to close, I just want to mention a couple other topics. So I've talked about a couple of game theoretic approaches to voting, but there are also some those are from non-cooperative game theory. There's also some work on cooperative game theoretic approaches to voting. There are some other problems that people are interested in voting. There was this control problem that I skipped over. Another one is the possible necessary voter problem, possible necessary winner problem, which is given that you already know some of the votes, which alternatives are still able to win. Okay, this is relevant, for instance, when you're eliciting votes. You're some part of the way through. can you now already declare a winner, or do you need to elicit more information? Again, social choice is not restricted to voting. There are a number of other interesting topics. One is judgment aggregation. So in judgment aggregation, we have a couple of judges and a couple of propositions, and the judges have to figure out which of these propositions are true or not, and they have their own opinions. So individually on the propositions, they could vote. But the problem is that the propositions might be logically related to each other, and so we don't want a logically inconsistent outcome, which could happen if you vote on the issue separately. And so then how do you come up with rules that do guarantee you a logically consistent outcome that still makes sense? Allocating resources to agents. Well, we've heard Hervé give part of his talk about this already, and so I'll defer to that. Matching, we've heard Itai talk about. Coalition formation, this is the problem where you have a set of agents that can work together in various ways, and so how do you partition them into coalitions in such a way as to get maximally good outcomes? There's a lot of other cooperative game theory work. I think one direction that's very interesting and that should be getting more attention is the notion of ranking systems and their relation to social choice. Right? You can think of something like PageRank, or something like a social network where people vote for each other by linking to each other, and based on this, maybe we want to rank the different nodes of this graph. Right? So that's one thing that PageRank does, and there are other ranking systems like that as well. It's not quite the same as this voting setup, but there are a lot of similarities to it. And can you use these kinds of axiomatic approaches? People have made some good beginning results, but with one of the main authors going to Google, it's been ignored a little bit, I think, at this point. And I think it deserves not to be ignored. It's an interesting topic. And finally, there's a lot of literature on tournaments. So tournaments play a role in some of the rules that we've seen based on pairwise elections, but you might also think about sports tournaments, right? And so how do you design sports tournaments? How might sports tournaments be manipulated? And so on. There's some work on that as well. Okay, I'm actually going to end here. Any questions? Yes?
You used Kemeny rules in deciding the establishment judgment, and you said that in those cases you had particularly nice instances where this program is actually tractable, right? Or
right. So, well, by the way, first of all, I should clarify that we didn't just take the top K of the Kemeny ranking, right? So what we really use this for is we use it for projecting the list of candidates on the board for the final admissions committee, and then we went from the top. We went from the top, and it was admit, 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 and then we went from the bottom, and it's reject, 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 and then there's kind of the hard middle. Anyway, so
right. So is there? Can you say anything more formal about this? Like, can you characterize the class of instances on this?
Yeah, that's interesting. So there is. This observation I was making was just totally informal, but roughly the idea. This idea that if you have a lot of agreement in the votes, it gets easier. That's been noted a couple of times, just certainly from experimental work. But there is some nice work on a kind of a fixed parameter tractability of Kemeny ranking, right? So one way to formally figure out where the easy instances might lie is you might be able to prove that here's an algorithm for an NP-hard problem. Unsurprisingly, it's going to have exponential runtime, but it's going to be exponential only in this one parameter of the problem, right? So you can show that if this one parameter of the problem is small, then your runtime, if it's bounded, then it would your runtime would be polynomial. And there are some formal results along that line by Nadja Betzler and others. What's that?
Can you extract some parameters?
Yeah, so there are some parameters for which it's known, and roughly they have a similar flavor as well in terms of not having too much disagreement. Right? I can give you the references to see what actually the specific parameters are. Right? But so there is some work along that, and I think that's actually a nice approach, not just for this problem, but in general, right? Like trying to figure out what parameter of the problem really makes the problem hard. And I think with Kemeny ranking, I think we really do have a good sense that, in some sense, the more that the voters agree with each other, the easier the problem becomes, and really it becomes easier quite quickly. So that's nice. But yeah, if you take uniformly random preferences, then it actually scales very poorly. Or at least the current solvers, well, at least some number of years ago, the solvers did not scale well.
So what sort of axiomatic problems do you get if you switch to, I guess, cardinal rankings? Or if you allow like numbers in your ranking system, right?
Then
I mean, are there sort of axiomatic problems that always show up, or I mean, it seems.
Oh,
kind
you're
of,
saying like
yeah.
so if you're able to say I give this alternative a score of 100 and this alternative a score of 95, or right, and you can pick whatever score you would like, right? So that's one possibility, and some people propose this. I think so. There are a couple of downsides to that. One is that you actually have to think about scores. It also really invites strategic behavior, right? That you say, well, you might imagine that in the limit you're going to give some alternatives a score of 100 and some a score of 0 to try to help as much as possible. In that case, it gets kind of meaningless, or you're kind of just back at approval voting. But people have very vicious debates actually about those kinds of issues. Now, of course, if you can have side payments, right, then everything is easier. Right now, you can just use VCG again. But typically in voting, you don't want to have side payments. And if you don't have side payments, it's very difficult to get kind of strategy-proof reporting of intensity of preference, right? But what you would really like to express with this kind of situation is that not only do you prefer A to B, but you really prefer A to B, right? And if you allow for payments, then you can actually get this because you can actually say, okay, well, if you reported that you really liked A a lot better than B, and we chose A because of that, and if you had reported a slightly less strong preference, we wouldn't have done it. We're going to make you make a large payment, and so that gives you the incentive not to abuse that power, right, of reporting intensity. But if you don't have payments, it gets very hard to have strategy-proof reporting of intensity, right? Because there's going to be a tendency to over-report, just to say that, well, this is, the gap between A and B is as large for me as it possibly could be, even if it really isn't. That being said, there may still be some value to do it.
So I think you mentioned there's a control problem that you kind of skipped maybe. I just want to know maybe briefly what it is about, if that's possible. I'm not sure if there's enough time. The control problem that you
Okay, yeah, I can quickly talk about that. Let me see. I skipped over it because I thought I was running out of time, but that was actually okay. This is a slightly different type of problem. So instead of voters manipulating the election by casting strategic votes, you can think about other types of undesirable behavior. For example, you might have the chair of an election who has some control over which alternatives run, right? Maybe there are some alternatives that she has no control over whether they run or not, right? So maybe there's 5 possible alternatives, A, B, C, D, E. Everybody is expecting A and B at least to run, so the chair is not able to prevent them from running, but the chair has, let's say, control over which of C, D, and E run, and the chair might be able to use that in order to make her most preferred alternative between A and B even win, right? So here's a specific example where suppose that you know that these are going to be the preferences of the different voters over all of the alternatives, right? But the rule is going to be plurality, and if you're the chair, you get to prevent any subset of C, D, and E from running, right? And thereby it might actually affect the outcome, right? For instance, if you remove D, that's going to give you another vote for B here, right? And so then the question is, well, given a set of votes and some subset of the alternatives over which you have control whether they run or not, can you make a specific alternative win? Okay. So we might as well do this example. So can you do it here? Somebody see. Right, so if the chair lets everybody run, actually A ends up winning, right? But the chair wants B to win. How do you do it?
Just don't allow D.
Yeah, exactly. You just take out D. Now B is going to get 2 more votes. That's going to do it. Okay. So this is NPR, and so again, you have this argument that, well, this might be a good thing, that computational complexity prevents manipulation by the chair. But again, it in principle falls prey to all of the same issues that, well, NP hardness means there are going to be some hard issues. That doesn't mean that there aren't algorithms that solve it most of the time. Right? Less formal work has gone into actually proving that that's the case, that there are these algorithms that usually work, but I don't see any reason why that wouldn't be the case. Any more questions?
Alice, thank you for your response.